Hello students, in this lecture we are going to learn how do we balance the redox reaction. In this particular lecture we are going to deal with the oxidation number method of balancing redox. Right now, if you are going to balance a redox reaction, there are two ways by which you can balance a redox. First one is oxidation number method, and the another one is half reaction method. This is also known as ion electron method. This we'll see in the next lecture. Currently, in this particular lecture, we are going to focus on oxidation number method. So may it be any method of balancing the redox, there are two things that you need to keep in mind. That you have to follow the law of conservation of mass. Second thing is, you also have to follow the law of conservation of charge. In the normal reactions, you just follow the law of conservation of mass, but in redox, you have to follow this also, right? So keeping in mind, we'll proceed forward. Okay, so what are the prerequisites for this reaction? First thing that you will always do while balancing the redox reaction is that always split an ionic molecule into ions. This is the first thing that we are going to do always, whether it be oxidation number method or the half reaction method. We will split the ionic molecule into the ions. First thing. Second thing, we need to know about the spectator ion or the molecule. What are they? They are the ions or molecule which does not participate in redox. How do you identify whether something is participating in redox or not? You identify using the oxidation number. If you see if someone is changing its oxidation number or not. If someone is changing its oxidation number, it is participating in redox. If it is not, it's not participating in the redox, right? So we will always remove spectator ions. Always remove the spectators while you have started balancing, right? Later on, once you have balanced, in balanced redox, bring back the spectators. How? We'll see that. How we are going to bring them back, this particular step we'll see while we are balancing, right? So we'll keep this in mind. Next thing is that, so this was about the spectator ions or spectator molecules. Next thing is the medium in which the reaction occurs, right? So there can be three types of medium in which a redox reaction occurs. It can be acidic medium, it can be a basic medium, or it can be a neutral medium, right? So acidic medium is in anywhere in the reaction. If you see H plus or any acid anywhere in the reaction, it may be on the reactant side also, it may be on the product side also, it may be provided over the arrow also. So that represents acidic medium. In the similar way, presence of OH minus or any base in the reaction in the equation represents the basic medium, and neutral medium you will not find H plus or OH minus, it's absent. You will just find water molecule over there. One more thing, presence of water molecule is mandatory. Why is it mandatory? Because any ionic molecule will split into ions in water only, right? Next, now let's start our oxidation number method. So before proceeding to this, you must be aware with the oxidation number. how do we find the oxidation number. So there is a separate lecture for oxidation number. So you can refer to that video for how to know about oxidation number. This particular lecture requires the knowledge of oxidation number. Fine. So we'll start with an example with a question. Question is MnO4 minus with C2O4 minus 2 plus H plus gives us Mn plus 2 plus CO2 plus H2. This is a reaction, right? Now, let's see the rules over here. What are the steps that you are going to follow? Rules or steps. So first one is that assign oxidation number to each. First we are going to assign oxidation number to each. So manganese over here, if you calculate, is in +7 state. Oxygen and hydrogen usually we can avoid assigning their oxidation number, because most of the reactions they will not be changing their oxidation number, right? Carbon, if you calculate, you will get +3. Hydrogen is +1 already. Manganese over here in +2. This carbon over here in +4. Okay. If you check in this, here also oxygen is in -2 state. Oxygen over here in a -2 state. Hydrogen +1. Oxygen over here -2. Over here also -2, and hydrogen +1. So what do we see? That hydrogen is nowhere changing its oxidation number. So H plus ion is the spectator ion, right? We can remove the spectator ion. Another thing, is water a spectator molecule? Yes, it is a spectator molecule because it is not a product of a redox reaction, right? So we can remove them. They will come back in the balanced equation. You don't need to worry about the spectator ions or the spectator molecules which you have removed. Second, in second, you will balance only those atoms which are undergoing change in oxidation number. Balance only those which are undergoing change in oxidation number. So after removal of H plus, can I rewrite this equation like this? MnO4 minus plus C2O4 minus 2 gives us Mn plus 2 plus CO2. Right? CO2 is a covalent molecule that cannot be splitted. MnO4 minus can also not be splitted into manganese and oxygen, right? That is why we have kept it in their form only. Fine. Manganese over here in the +7, as we have seen. Carbon +3, manganese +2, and carbon +4. Right. What do we see? Manganese is showing the change in oxidation number, and also the carbon is showing change in oxidation number. Right? So we will balance only those atoms in this step which are undergoing change in oxidation number. So manganese, if you check both sides, it's already balanced. Both sides we have 1 manganese, right? But if you check the carbon is not balanced. On the right hand side we have just 1 carbon. On the left hand side we have 2 carbons. So we will multiply it by 2. Carbon is balanced. Remember, in this step we will balance just the atoms undergoing change in oxidation number, not all other atoms. Fine. Now in the last step we got this equation, MnO4 minus plus C2O4 minus 2 gave us Mn plus 2 plus 2 CO2. That is what we got. Now what is the third step? Third step is calculate change in oxidation number per molecule. You have to calculate the change in oxidation number per molecule. Usually oxidation number is charge per atom, right? That's how you define oxidation number. It's charge per atom. But what you have to calculate over here is the total change that one molecule will be showing. For example, manganese over here in the +7, over here +2. If you calculate the change in oxidation number, there is just 1 atom of manganese which is undergoing change in oxidation number in 1 ion of MnO4 minus, right? So change over here per atom change is over 5 unit. And also per molecule have just one atom of manganese, that's why change is 5 only. Here we don't have any problem. But the main problem arises over here. If you check, carbon over here is in the +3 state, over here in the +4 state, right? Oxidation number +3 in C2O4-2 is shown by each carbon atom over there. Each carbon atom over there shows +3 state, and in CO2 each carbon atom over there shows +4 state. So change per atom is by 1 unit. One carbon atom, each carbon atom is showing a change of 1 unit, but there you have 2 carbon atoms and both carbon atoms are participating in the redox. So if one carbon atom gives a change of 1, a molecule contains 2 carbon atoms, so a molecule will be giving a total change of 2 units, right? Per atom change is 1 unit, but per molecule contains 2 carbon atoms and both carbon atoms are showing the change of 1 unit. So total change that per ion of C2O4-2 is giving to us is 2, right? Now what do we understand by the change in the oxidation number? That is important to understand, right? Okay, so loss of electrons will increase the charge. We know that it will increase the charge, or we can also say that it will increase the oxidation number, right? And gain of electrons will decrease the charge, and so it will decrease the oxidation number also, right? So if we ignore increase or decrease, basically change in oxidation number of 1 unit is because of transfer of 1 electron. If there is a change in oxidation number by 1 unit, if the oxidation number is increasing by 1 unit, we will say that 1 electron was lost. If there is increment in oxidation number by 2 unit, we will say that 2 electrons were lost. 3 unit, we will say 3 electrons were lost, right? So for example, in the first case, second case is the oxidation case. We see that carbon is undergoing oxidation over there. We don't say carbon is undergoing oxidation, we say C2O4-2 is undergoing oxidation, fine. But there carbon shows a change of 1 unit per atom, right? Per molecule the change is by 2 unit. What does that mean? That there is an increment in the oxidation number by 2 units. So can we say that this molecule of C2O4-2 has lost 2 electrons? Then only you can get a change of oxidation number by 2 unit, right? For example, let's take an example more evident. Suppose iron, if it loses 2 electrons, we say iron is undergoing oxidation and it forms Fe+2. Check the oxidation number. Iron over here in the free state, that is by 0. Over here monoatomic ion, so +2. What is the change in the oxidation number? Is it 2? The change in oxidation number is by 2 unit, right? So does that also mean that iron lost 2 electrons? Then only there was change in oxidation number by 2 unit. Same thing happens in case of when someone gains the electron. For example, suppose that Fe+3 gains 3 electron. Will it become Fe? Right? Fe+3, if it gains 3 electron, you see the oxidation number changes by 3 unit. Changes by 3 unit, right? It has decreased over here. It has undergone reduction, right? Why there was change in by the 3 unit? Because it gained 3 electron. So transfer of 1 electron and it accounts for change in oxidation number by 1 unit. We'll keep that in mind. Fine. So change is by 5 unit. That means over here MnO4-2 Mn+2. That is the reduction process. We can see manganese is decreasing its oxidation numbers. That means 5 electrons were gained by MnO4-, while in case of C2O4-2, in this case, can we say that change of 5 unit means 5 electrons are gained? If change is by 2 unit, and that is the oxidation process, so we can say that 2 electrons were lost. Now question is, the number of electrons lost were 2, but the number of electrons gained were 5. That is not possible, right? So number of electrons lost must be equal to the number of electrons gained. And how can we make them equal? If we make the changes equal, the number of electrons lost will become equal to the number of electrons gained. So in the fourth step, we will make the change in oxidation numbers equal. And how will you make it equal? By multiplying by the suitable number. And how can you find the suitable number? If you take the LCM of the two changes. So if you take the LCM of 5 and 2, the LCM is 10. If you take the LCM of 2 and 5, the LCM is 10. So if you multiply this by 5 and this by 2, the changes will become equal, right? Right. Now one pair of MnO4 minus 2 Mn plus 2 is giving you a change of 5. So for if you need the change of 10 unit, we will multiply by the same number to the same pair. 2 MnO4 minus gives us 2 Mn plus 2. And 5, we have multiplied 5 for the change to get the change of 10. We will multiply it to the same pair. 5 over here. And this 5 into 2 will become 10. Right? So can we write it as 2 MnO4 minus plus 5 C2O4 minus 2 gives us 2 Mn plus 2 plus 10 CO2. That is what we got in the last step by equating the oxidation number change. Fine. Now we have balanced, we have equated the change in the oxidation number. Now in the fourth step, balance the charge. Now how are you going to balance the charge now? It's different for different medium. For acidic medium, use H plus to balance the charge, right? Now why are we going to use H plus? It's not a foreign particle, it's not any random particle that we are going to add to the equation. It was already present over there. If you could see in the question, it was given, the H plus was present over there, right? We are just bringing it back. H plus signifies the acidic medium, so it's that reaction was occurring in the acidic medium, so H plus is already present there, right? So we'll use H plus to balance the charge in acidic medium. But if it is a basic medium, so in basic medium OH minus ions are present, so use OH minus to balance the charge. So we'll see it when we are practicing the basic medium problems. For now, let's calculate the charge on both sides. So from 2 MnO4 minus, do we have minus 2 charge? From 5 C2O4 minus 2, do we have minus 10 charge? From 2 Mn plus 2, do we have plus 4 charge? And do we have 0 charge from the CO2 molecule, right? So total charge on LHS side is minus 12, and total charge on the product side is plus 4, right? Now we have to use H plus to balance the charge, right? Now H plus, what is H plus? H plus will always increase the charge. Whichever side you add H plus, it will always increase the charge because it has positive charge, right? So which side we should add it to? We should always add H plus to the side deficient in charge. Because if you add H plus to the side which already has the excess charge, it will further increase the charge. It's not going to balance the charge, right? For example, plus 4 charge is there on the RHS and minus 12 charge is there on the LHS. So even if you add 1 H plus on the right hand side, it will become plus 5. It's not going to balance, right? No way it's going to balance the charge if you add it to the side which has excess charge. So you will always add H plus to the side which is deficient in charge, and there is a logic also, right? Now question is how many H plus we should add. See, minus 12 over here and plus 4 over here, right? So if we add 16 H plus over here, will we have plus 4 each side? Now you can check. From 16 H plus, we will have plus 16 charge, and we already had minus 12, so total will be plus 4. Both sides charge is balanced. So we will add appropriate number of H plus to the side which is deficient in charge. So we added 16 H plus. Fine. So this is how you balance the charge. Now next. So it was 2MnO4 minus plus 5C2O4 minus 2, and we added 16H plus. It gave us 2Mn plus 2 plus 10 CO2, right? Now in the fifth step, balance oxygen now. How you balance oxygen? Water was already present over there, right? So we will balance oxygen, and we had removed water, if you remember. We call it a spectator molecule and we removed it. We need to bring it back now. So balance oxygen using water molecule. We see one water molecule contains one oxygen, right? So for each lacking oxygen, for each lesser number of oxygen, we are going to add one water molecule to balance it, right? So if you have 8, there is a difference of 8 oxygen atoms both sides, you will add 8 water molecules to the side deficient in the oxygen. For example, let's calculate the number of oxygen atoms. From this we have 8 oxygen, from this we have 20 oxygen, and then we don't have any oxygen over here. So total oxygen on the LHS side is 28. On the RHS side, we have the oxygen is there, present there in just CO2, so we have 20 oxygen present, right? Now if you see, the LHS side has 8 extra oxygen, right? So if we add 8 water molecule to the side deficient in oxygen, the oxygen is balanced now. Both side has 28 oxygen now. Oxygen is balanced, and after this step, hydrogen will automatically get balanced. So if you check, hydrogen is balanced. You have just 16 hydrogen on LHS and you have 16 hydrogen over here. Hydrogen is balanced. Fine. So this was the question in the acidic medium. So this is your balanced equation. If you have to write it finally, this is the balanced equation. This is the balanced equation. If you see, the spectator molecules and ions are back. Anyway, now how do you check if your redox reaction that you have balanced is correct or not? So first, check if all the masses are balanced or not. Then you check if all the charges are balanced or not. So if the law of conservation of mass and law of conservation of charge, if these two are satisfied, your redox reaction is correct, right? So for example, you see 2 manganese, manganese is balanced. 10 carbon is balanced. Oxygen we have already balanced. 8 from here, 20 from here, 28 oxygen. 20 from here and 8 from here, 28 oxygen balanced. 16 hydrogen balanced. So law of conservation of mass is being followed in this. Next, let's check if the charges are balanced or not. Minus 2 from here, minus 10 from here, minus 12 plus 16 plus 4. On the right hand side, plus 4. Charges are also balanced. So this is the correct balanced redox reaction. Let's take one more question in the basic medium. So in the basic medium, we are going to use OH minus instead of H plus. So for example, question is MnO4 minus plus SO3 minus 2 plus OH minus. It gives us MnO4 minus 2 plus SO4 minus 2 plus H2O. So we can always remove the spectator ions. Let's remove OH minus and H2O. So we get this equation, MnO4 minus plus SO3 minus 2. It gives us MnO4 minus 2 plus SO4 minus 2. Right. Now assign the oxidation number to each. Manganese is plus 7. We are avoiding assigning oxidation number to oxygen because in majority of the time it will not be participating in the redox. You will assign oxidation number to oxygen only in the case when you know there is a peroxide and it's changing to oxide or normal oxygen molecule, right? Sulfur over here is in plus 4 state, manganese in plus 6, and sulfur in plus 6. Now balance the atoms undergoing change in oxidation number. So manganese is undergoing change in oxidation number, it's balanced. Sulfur is undergoing change, it's balanced. Now calculate the change per molecule. So per molecule has one manganese atom only, right? So per atom change and per molecule change will be same. So change over here is by 1 unit. It goes from +7 to +6. So change is by 1 unit. For sulfur, the change again the same thing. Per molecule or per ion has the same one number of atoms only. So change per atom or per ion will be same. So change over here is by 2 unit. Make the changes equal. So if we multiply this by 2, the changes are equal. So for that we need to multiply to the pair. Changes are equal now. Now you balance the charge. So if you calculate the charge, you get -2 from here and -2 from here. So total charge on the left hand side is -4. On the right hand side you have -4 from here and -2 from here, -6. Now OH minus, it carries the negative charge. It will always decrease the charge. It will always decrease the charge. So you should add it to the side which is having excess charges, the appropriate number of OH minus, right? So if you compare -4 and -6, -4 is greater than -6, and if you add 2 OH minus this side, the charges will get balanced. So charges are balanced now, and so the spectator ion that we removed is back. Next, balance oxygen. 8 oxygen from here, 3 here, total 11 plus 2, 13 oxygen. On the right hand side, 8 oxygen plus 4, 12 oxygen. So if we add 1 H2O, oxygen will get balanced. Check hydrogen, hydrogen automatically gets balanced. 2 hydrogen, 2 hydrogen. This is your balanced redox reaction. So balanced one will be 2 over here and 2 over here, 2, and that's it. That's the balanced redox reaction, right? So this is how you balance the redox reaction using the oxidation number method. Let's see a bit complicated problem. So question is K2Cr2O7 plus H2SO4 plus Ki. It gives us I2 plus K2SO4 plus Cr2SO4 whole 3 plus H2. First thing is that you split it into the ionic form, right? So K2Cr2O7 can be written as 2K plus Cr2O7 minus 2, right? Plus H2SO4 can be written as 2H plus SO4 minus 2. Then Ki can be written as K plus I minus, giving to I2 cannot be ionized, that's a covalent molecule. K2SO4 can be ionized into 2K plus sulfate ion. Similarly, Cr2SO4 whole 3 can also be ionized as Cr plus 2 plus 3 plus 3 sulfate ion. Water cannot be ionized. Now, this time we have more number of spectator ions. It's beyond hydrogen and water this time, right? What are the spectator ions? If you can identify, potassium is nowhere changing its oxidation number. It's not changing its oxidation number anywhere. So we'll simply remove K plus now. Let's remove K plus. Its spectator, will bring them back later on. So K plus removed. If you check, hydrogen is also not participating in the redox anywhere, so we removed H plus. Sulfate ion also is not changing its oxidation number anywhere, neither sulfur nor oxygen of the sulfate ion, right? So it's also a spectator, we will remove it. Water we can remove, right? Now we are left with just this equation now. Cr2O7 minus 2 plus I minus gives us I2 plus Cr plus 3. I have removed these numbers. We'll get back that when we are balancing it now. So first thing is that we need to identify the medium. So it's an acidic medium problem because an acid was present over there, right? So it's an acidic medium problem. Now start balancing it. Chromium over here in the +6 state, iodine -1, iodine 0, chromium +3, right? So let's rewrite it on the next page. Cr2O7 minus 2 plus I minus gives us I2 plus Cr plus 3, right? So let's once again assign the oxidation number, plus 6, minus 1, 0, and plus 3. Balance those atoms which are undergoing change. So chromium balanced, iodine balanced, right? Now calculate the change per molecule. So for chromium, per atom change is from plus 6 to plus 3 by 3 unit, but per ion or per molecule over there are containing 2 chromium atoms, so the change will become double, so change is by 6 unit. For iodine, the per atom changes from minus 1 to 0 by 1 unit, but there are 2 iodine atoms which are participating in the redox over there, so total change will be by 2 unit, right? The changes will become equal. Over here it's 6 unit, over here 2 unit. If we multiply it by 3, the changes will become equal. So this has to be multiplied by 3. Same way this also has to be multiplied by 3. So we get this Cr2O7 minus 2 plus 6I minus gives us 3I2 plus 2Cr plus 3. Now balance the charge. Over here minus 2, over here minus 6, total minus 8 charge on the left hand side. On the right hand side we have plus 6 charge, right? It's plus 6, on the left hand side minus 8. So if we add 14H plus on the left hand side, the charges will get balanced, right? The charges are balanced now. Now let's balance the oxygen. We have 7 oxygen over here, but no oxygen on the right hand side, so we can add 7H2O. Oxygen is also balanced. If you check, hydrogen is also balanced, right? So this is the balanced redox reaction now, but we need to bring back those spectator ions which we have removed, right? So let's rewrite the equation as Cr2O7 minus 2 plus 6I minus gives us 3I2 plus 2Cr plus 3 plus 7H2O. This was our balanced equation, and there was 14H plus also over here. Fine. Now we need to bring every atom back whichever we have removed. So if you can check in the original equation given, Cr2O7 minus 2 was bonded with potassium, right? It was in the form of K2Cr2O7, right? So what do we see? 2 potassium ion goes with 1 Cr2O7 minus 2 if you apply the mole concept. 2K plus goes with 1 Cr2O7 minus 2, and since we have just 1 Cr2O7 minus 2, so we must add 2K plus, but we should add it both sides. Why we need to both sides? So that the balance that we have done so far is not disturbed, right? Okay, so does this become K2Cr2O7, fine, plus I minus was originally present in the form of Ki, right? We see 1K plus goes with 1 I minus, so 6I minus will go with 6K plus, but we need to add 6K plus both sides, again for the same purpose, that whatever balancing is done so far is not disturbed, right? So 6I minus and 6K plus, does that become 6Ki? Yes, it becomes. Now H plus was present with H2SO4, right? We saw that 2H plus was combined with 1 sulfate ion, so 14H plus must have combined with 7 sulfate ion, and again we need to add sulfate ion to both sides. Fine. So 7 sulfate ion and 14H plus will give us 7H2SO4. So we are done with the left hand side. Now let's go on the right hand side. Right hand side 3I2 is in the original form. There is no problem with that. But Cr, chromium was present with the sulfate ion in the original equation in the form of Cr2SO4 whole 3. So what do we see over there is that with 2 Cr plus 3 sulfate ion was bonded with. And we have just 2 Cr plus 3. So with 2 Cr plus 3, the 3 sulfate ion will get bonded. So we had 7 sulfate ion in total. Out of 7, 3 will go with Cr plus 3 to give us 1 Cr2 SO4 whole 3. Out of 7 we have used 3, we are left with 4 sulfate ions, right? So other sulfate ions was present with the potassium in the form of K2SO4, right? So we saw there that 2K plus goes with 1 sulfate ion. So the 4 sulfate ion will go with 8 potassium ion, and we have 8 potassium, 2K plus plus 6K plus. So we should get 4 K2SO4 and then 7H2. So this is how you bring back the spectator ion that you have removed while balancing the equation. So this is your balanced redox reaction. So you will bring back the spectator ions using the mole concept. In whichever form they were present originally, in the same form you have to give back in the balanced equation. So in the next lecture, we will be seeing how do we balance the redox reaction using half reaction method.